This is the end of the line. This is the very, very last thing we're going to be looking at. This is the relationship between the equations and the graphs of polynomial functions and equations. Okay, so we've done lots of these things before with like parabolas and quadratics, but now it's just going to be any polynomial in general. So just like quadratics, the zeros of a polynomial function, right? A polynomial function is like y is equal to something, right? Y equals some x squared. They correspond to the x-intercepts of the graph, and they're also the roots of the equation. Now, the equation is going to be some function equal to 0, okay? So a function typically usually means y equals some function, y equals f of x. However, the equation would be the equation equal to, like the function, whatever this is, equal to 0. This is x and y, this is just one variable. So if you have something like this, f of x is equal to this. So this is like saying y, right? We know that this can be factored into f of x is equal to x plus 3 and x minus 2. Remember? Right, two numbers are multiplied by 6 and add up to 1. So they have to be side by side, 3 and 2. One's positive, one's negative. So that's the exact same as this. It's just in a different form. So this equation, right, this thing is going to have answers, or in other words, they call it has roots, or in other words, we call them answers. X is equal to negative 3 and positive 2. X equals negative 3, x equals positive 2. Remember, that's using the zero principle. In order to make 0, this would have to be positive 2, 2 minus 2. So this thing has roots there. However, this function, I shouldn't say it has roots because every possible xy point in that works on the function works. However, it has zeros. So we talk about the zeros. The roots and the zeros, really, we kind of mean the same thing. That means there's only two of them. Like there's a whole bunch of, there's an infinite number of x and y points. But these things have zeros. X is equal to negative 3 and x is equal to positive 2, right? Those are the zeros of the function. Okay, so in the same way, you've got this polynomial. Well, this one's already factored, which is fantastic, right? This thing is the factored form. Now, if we had all expanded it all out, it would have been this. It would have been f is equal to, I know it starts with an x cubed, xxx, and it's going to be negative 1 times negative 1, which is positive times, I know it's going to be plus 2 on the end. It is. So you can tell that just by looking at the factored form. Now, if we expand this thing all out by FOIL and superFOIL, yep, that's exactly what you would do. You would end up getting this, minus 3x plus 2. So that's the exact, so this was normally what you were going to be starting with. This is the factored form. So I know that this equation, right, it has roots. In other words, it has answers. X is equal to 1, negative 2. Positive 1, x equals negative 2. So in other words, if I was to graph this thing, and we will, it's going to have two zeros. It hits at positive 1 and negative 2. So this thing has zeros, or x-intercept. X equal to positive 1 and x equal to negative 2. Okay, so notice in this factored form, the x minus 1, it's a double factor. In other words, they say that this has a it has a multiplicity of 2. It's there twice. We call it a double root, right, or a double factor. This one is a single factor, right? It's only there once. So yeah, that would be a multiplicity of 1, right? So the nature of the graph and the zeros, they change with their multiplicity. So if you have a 0 of 1, right, or a multiplicity 1, that just means it's a regular root. So in other words, something comes from here to here. That's a multiplicity of 1, right? So in other words, they could also say the function f of x changes sign. Huh? What do you mean? Well, it goes from above to below. Oh yeah, so that's a root. That's a 0, if you will, right? And they would say this is order 1. If you had multiplicity of order 2, right? Something that's multiplicity of order 2, That would be this case, where it's tangent, and then it goes back up. Oh yeah. Remember, this is a critical point. And they would say f of x doesn't change sign. It goes from positive to still positive. Doesn't change sign. Yeah, so a multiplicity of 2 is a double root. Oh yeah, so these are our tangent points, critical points. So what does a multiplicity of 3 look like? Well, it's going to come down, right? And it's going to cross over, but it's going to change its curvature. This is an inflection point. Yes, this is what an inflection point really is. But in the equation, it would be something with a multiplicity of 3. So f of x changes sign. Yeah, it does. Changes sign. And curvature changes. We're allowed to call this an inflection point. However, the textbook would never use the phrase inflection point because people don't know what that is. We know that this is an inflection point. We know that this is a critical point, right? So if you look at the equation, if it has a multiplicity of 2, it's going to be a root like this. And you know what? If you were to quickly do derivatives and stuff like that, you would find out why, right? So now you can describe the graph's behavior using multiplicity of the zeros, multiplicity of the zeros. Yeah, we call them a single zero or a double zero or a triple zero, whatever. And also the x and y intercepts. Oh yeah, the x and y intercepts are they're easy points to figure out because you plug in x value of 0, you get the y intercept. You plug in the y value of 0, you get the x intercept. What else? We can also figure out the leading coefficient, right? Is it a positive or a negative? The leading coefficient, as well as the minimum degree, right? What do you mean? We can tell from the shape of something. Is it a degree 2, degree 3, degree 4? Remember even degrees, whatever happens in between, they both go in the same direction. Both the left and the right behavior will be in the same direction. However, odd degree polynomial, I don't know what happens in between. I know they're going to be opposite. Guaranteed. So you can tell if it's even or odd. Okay, so here is a polynomial function. Okay, so this thing goes down to infinity. They really should have put zeros on or arrows onto their graph because once you get the arrows, basically that's telling you, yeah, this thing doesn't change direction again. It just goes down to infinity. It keeps on with the same curvature, etc. So this thing has 1, 2, 3 turning points or critical points, if you will, right? Three bumps, which means it's got to be minimum degree 4. So the least possible degree, it has to be at least 4. Maybe it's 5, probably not, because these are in the same direction. But it could be 6, right? It could be degree 6. I don't know. Depends, who knows. But I know it can't be degree 2. A degree 2 is going to look like a parabola, and this is certainly more complicated than a parabola. So sine of the leading coefficient, look at the right-hand side, goes down to negative infinity. It must be negative. It has to be negative. Now, I'm only looking at the right-hand side because it only tells me this. And the reason why, if they ask you to explain why, well, because the limit as x goes to positive infinity of f of x is negative infinity, right? We know that. But you'll never see this notation in the textbook. So what are the x-intercepts? It hits the x-axis at negative 5, 0. Give it to you as exact. Negative 1, 0. And also 4, 0. So the x-intercepts and the factors with the least possible, hang on, x equal to negative 5. This is a multiplicity of 1, right? X equal to negative 1. That's also a multiplicity of 1. It's not changing concavity. Careful, we don't know the word concavity, but it is crossing over. This one is multiplicity of 2. I know that. And so positive 4, it's a multiplicity of 2. Multiplicity of 2. So it's a double root. I can tell from the shape. So what are the factors? Well, this thing is probably going to be like this. So hang on. Let's get rid of that. My function is probably going to be x plus 5 minus 1. X plus 1 and 4. So it's going to be x minus 4. And the x minus 4 is squared because it's a double root. So I don't know what this number is, but I do know that it has to be negative because, well, let's find out. So let's figure out the intervals where this positive and intervals where it's negative. So once again, we're talking about the function. Where is it positive? This section right here. This is where it's above the x-axis. That's it. So from -5 to -1. So positive is from -5 to -1. Are we including the points? No, because that's where it's actually equal to 0. So we shouldn't include these points. 0 is not positive. It's certainly not negative, but it is not positive. Okay, and where is it negative? Well, it's negative from here down to infinity, so from -5 and off to the left. So it's going to be from -infinity up to -5, never inclusive. So from -infinity up to -5. It's also negative from -1 to +4, -1 to +4, and also from 4 on to infinity. Do I really have to, couldn't I just say from -1 up to infinity, right? Doesn't that really just all come together? Like, wouldn't that make sense? Can we grab this thing? Yay. Yeah, so from -1 on to infinity, yes, except for this one point. So if I did want to do this interval, I would have to stipulate, oh yeah, by the way, I have to say, by the way, x is not equal to +4. Otherwise, I do need to do it as two intervals, right? It's not that hard to do it as two intervals. -1 to 4, and then from 4 on to infinity. That's the negative. But at the x value of 4, it's not actually negative. It is 0. Okay, so what is a possible equation? Well, this is our possible equation we had here, right? We said f of x, oh, let's not do that like that. F of x is going to be, it was x plus 5, x plus 1, and x minus 4 squared. And I don't know what this value is, but I'm going to call it k. Now, if I actually knew an x and y point, I could figure out what k is. That's the whole idea. I know it's got to be negative. Now, it said a possible equation. So you know what? This is kind of good because you've demonstrated, look, you know the three roots, or the three zeros. There, -5, -1, +4. You know that this one's a double root, and you do know that this has to be negative. Now, you don't have to say negative k, because k could be a negative value in the first place. Doesn't mean that k is positive if you just write k, right? We don't know what it is. Now, if it actually says give the equation, not a possibility, but the actual one, then they want you to figure out k. And that's where you need to know another x and y point. Not that one, not that one, that one, that one. You know what? The easiest thing to do, look for the y-intercept. What is y-intercept? It's like -4, right? No. What is this? Well, it's not very, very well defined on this graph. Usually they'll tell you an x and y point. 1, 2, 3, 4, 5. This is -120, which means these are counting by 24, right? 120 divided by 5 is 24. They're dividing by, so 24, 24, 24, 24. That's -96. Well, now, if I wasn't sure, I'd probably estimate that. I don't know, -90, something like that. But if I can actually say this is 120, 1, 2, 3, 4, 5, evenly spaced. So I do know the y-intercept is -96. Well, y-intercept happens when x equal to 0. Oh, x equal to 0 is wonderful to plug in here. Okay, so let's do it. Let's actually do this. The y-intercept, the y value is -96. 0 plus 5 is 5. 0 plus 1 is 1. 0 minus 4 is -4 squared, which is 16. So 5 times 16, which is 80. So -96 over 80 is whatever k is. That's my actual value. It's going to be some kind of decimal. -1 1/5. -6/5, I think, if you divide out 16. Good. I know that it's negative, and that's the actual value that I could sub back in here. Boop. Right into there. Because f of x is, okay, so it turns out to be -6/5, whatever. Like that's a pretty big estimate because they should tell me the exact value. The important part is, do you have the roots and do you have the multiplicity? Multiplicity of 1, multiplicity of 1, multiplicity of 2. Okay, so let's sketch these graphs. So how to draw these things without knowing what they look like? Well, I know that the zeros, in other words, where does it hit the x-axis? At +1, -2, -3. So it hits here, +1, hits here at -2, hits here at -3. Okay, so those are the first 3 points that I know. What else do I know? Is this thing going up to infinity or is it going down to infinity? I don't know. hang on, yes you do. It's positive, positive, positive. If I was to expand this all out, it would be starting with a positive x cubed. So, you know what? I do know that this thing is going to go up to infinity, positive infinity, because it's positive. This one starts with a negative. It'll end up going down, right? So this is a multiplicity of 1, so it's got to cross over. This is a multiplicity of 1. That's a multiplicity of 1. So these are all single roots. It's got to follow this kind of shape, and then it's going to end up going down because it's an odd degree polynomial, should go down to infinity. So really all I'm doing is I'm connecting the dots, but hang on. I can do this a little bit more accurately. What is the y-intercept for this one? I should do this down below because I'm running out of room. What is the y-intercept? In other words, when the x value is 0, plug in 0. I'm going to get 3 times 2 times negative 1. The y-intercept is negative 6. So I do know it hits here at negative 6. So I do know that point. Okay, so now it's a matter of let's just kind of connect the dots. It's got to come down here. It's got to go through there. It's got to cross over, cross over. Now, is this the absolute minimum? I have no idea. If I wanted to know, I'd actually have to find a derivative. So it may or may not be a critical point, right? So this is going to go down to here, and that's going to go up and down, something like that. That is good enough, because here's what we're looking for. Do you have the zeros in the right place? Do you have this? Do you have it in the right direction? The only way you could mess this up here is to have it in the other direction, right? So like that, but then if you had that, you notice you've got the wrong y-intercept, so you know that that one's wrong. Come on, get rid of that. So this is a good enough graph because we're looking for that point, that point, that point. What about the maximums and minimums? You need to know calculus stuff for that, and we don't remember calculus. You know what? I don't remember any of that stuff, so don't worry about the critical points. They're not important. Right now, the zeros are the important point. Okay, what about this one? This one has a 0 at negative 2, and it's a triple, and it also is positive 4. So let's put in my roots. I know it hits at positive 4. It's a single root, and it's going to hit at negative 2, and this is a triple root. Whoa, multiplicity of 3. This thing ends up going negative, going down to infinity. So I know it's a multiplicity of 1, so it's just going to cross over. And then it's going to do that. That doesn't look like, because I do know it has to go from positive to negative, but no, it's going to be changing curvature. This is going to be something like this. This is like an inflection point. Okay, so it's not that simple. Besides, I know it shouldn't look like a parabola. I need to figure out the y-intercept. Oh yeah, so if I was to plug in 0, right, I'm going to get 0 plus 2. So 2 cubed, which is negative 8, times negative 4, which is negative times negative. Oh, this is going to give me positive 32. Look at my scale here. There's 5, there's 10. Oh, it's going to be way off. You know what? Let's cheat. I need to change the scale. I'm not going to change the x scale because I like that. This is okay. 10, 20, 30, 40. Let's do that. Really, let's just change this to 10, 20, 30, 40, because I know 32, which is around there, there's my y-intercept, okay? So I'm changing the scale just because I need to. So changing one of the scales is going to affect the graph, but I'm just looking for a sketch. So I'm looking for, do we know this and this? Okay, so this is going to come down. So somehow this is going to be an inflection point. It's either going to look like this, that kind of change of inflection, or this kind of change of inflection. This is a polynomial, right? These things are not going to be vertical asymptotes or anything. It's going to look something like this. It's going to look more like the first one, not this one. So an inflection change, right? This is concave down, if you will. But this is going to go to there. Now I've got to come down to here, and it's going to change its curvature. So this is not a great graph. Really, if you want, oh yeah, that's a bad idea too. If you wanted a good graph, you would do all the stuff we did with derivatives and first derivatives and second derivatives, right? And where is it increasing? Where's it decreasing? Where's its concavity? That's where you really know. But however, this is a good enough graph for now because here's what I've shown. I know the zeros are negative 2 and positive 4. I know this is a multiplicity of 1, so it simply crosses over, right? That shape, it's not changing its curvature. This one's a multiplicity 3, so it's crossing over and it changes it's got to change its concavity. So in a regular Math 12 course, we would say it changes its curvature. So it's not simply like this. It's got to be something like that, right? They talk about a parabola being half up and half down, but this is that point, that point, that point. That's all we're looking for. Okay, what about this one? This one's not factored. Fine, let's factor it. Remember, here's how we factor. My possibilities are going to be plus or minus 1 and 2 and 4. That's it. So those are the only possible numbers that I can try. So if I try, if this is a polynomial, right, what's p of 1? If I plug in 1, I'm going to get negative 2 plus 6 minus 4, which, by the way, is 0. Excellent. So the first one works. Nice. So p of 1 is equal to 0, which means x minus 1 is a factor. I do know that that is a factor, which means I should be able to divide x minus 1 into this. Let's do it. So negative 2, 0x squared, 6, negative 4. Remember x minus 1, I'm not going to use minus 1, I'll use positive 1. So negative 2 comes down, negative 2, add them up. Negative 2, negative 2, add them up. 4. 1 times 4, 4, add them up. 0. Excellent. There's my remainder. So y, if I factor this thing, I know one of the factors is x minus 1. And I know the other one is this one. Negative 2x squared minus 2x plus 4. I can factor this. Let's divide out the negative 2. So this becomes negative 2, x minus 1. This becomes x squared plus x minus 2. This is a trinomial that I can factor. So x minus 1. Pew. So two numbers are multiplied at 2. So it's got to be 2 and 1, but plus 2, and so x plus 2, x minus 1. Hey, look, there's the x minus 1. It's a double factor. Let's just get rid of this. It's a double root. Okay, so there we go. So I know it's a negative polynomial. It'll end up going down. X minus 1, so it's going to have a root at positive 1. And it's going to have a root at negative 2. And that's this one's a double root, and that one's a single root. So I know it's got to hit at negative 2. I know it's got to hit at positive 1. Do I know the y-intercept? Psst, go back up to here. Remember, the y-intercept is when you plug in zeros for x. Oh, the y-intercept's negative 4. Nice. This number on the end is negative 4. I could have plugged it into here too, but it's just easier to say, look, I know it's negative 4. So this one is a single root. This one is a double root. So it's got to go from here to here to here, which means this is going to do something like that and then go back down. So it's a double root. It's tangent. This might be the absolute minimum, or it might not. So I can draw it either way. It doesn't really matter. Maybe this thing goes a little bit deeper. Who knows? But I do know that this goes through there, and it's a single root, which means it crosses over. There we go. So one's up, one's down. Yes, because I know it's a cubic, and it's negative. It should be going down to infinity. Good enough. There's my graph. All I care about is, do I have these 2 points? So yeah, if you were to actually graph this, I would make this a 3-mark graph. So 1 is for the roots. Right? Do you have the correct roots? Negative 2 and, well, actually, if this was a question, you'd probably get 2 marks for doing the factoring first, then the 3 marks for the graph. Do you have the roots? And are they in the single and double? Are they the appropriate multiplicities? 1, do you have the y-intercept? Because the y-intercept is really an important point. Without this point, I don't know which way, there's different ways of drawing this graph. I don't know if it's a minimum or max, or a minimum or not, but I do know it goes to that point. And the other thing is, do you have the correct shape? In other words, is it going in the correct direction? And are they in opposite directions? So first off, I know that it's a cubic. And second off, I know it's negative. So it's got to go down to infinity. So 1 is really the shape of the graph. How accurate is it? Doesn't need to be accurate. These are sketches, right? If you really want to be accurate, you use a graphing calculator. And now anybody can just plug it into a graphing calculator. That doesn't prove anything. Remember, when we're doing all this, I know you're going to be using your graphing calculator for figuring these things out, but remember, here's the marks. Here's what we're looking for. 1, did you list off the possibilities? Because that's always our first step. And then I know you're going to be plugging these into a calculator. Once you get 0, did you state x minus 1 is a factor? That's a mark, right? So if you don't put it down and you don't write it, you've lost a mark. This doesn't mean anything. I don't care about that. Here's what I need to see. I need to see x minus 1 as a factor. That's the second mark. Third one would probably be like for doing the synthetic division correctly. Well, actually, you can do it synthetic or the other way. It doesn't really matter. But third one's probably for getting the correct quotient. And then actually writing it out and factoring the quotient. So yeah, a factoring question here would be probably worth 4 marks. And the actual graph could be worth 3. Plugging it into your graphing calculator doesn't give you all the marks, right? You're demonstrating an awful lot here. This is a put it all together kind of question. Okay, now one last thing. Some people say, well, that's silly because just like parabolas, I know some basic points and I don't need to go through all these things for, I know how to graph my parabolas. I just go 1, 1, 2, 4, right? Yeah, and guess what? You get the shape of a parabola. We know that. That's easy to memorize. You can do the exact same thing with a cubic. You can. Okay, so an x squared has over 1 up 1, right? 1, 1. And then the second one is 2, 4, right? 2, 4. And there's my single points, right? And then I just make this thing symmetric. And guess what? You got the shape of a parabola. It's not that hard. That's the basic shape of a parabola. I think about 1 squared and 2 squared from my vertex. Okay, let's do the exact same thing for a cubic. Here's my vertex. If I go over 1, 1 squared is 1. 1, 1. Now if I go negative 1, negative 1 squared is negative 1. Oh yeah, it's going to be in the opposite direction. Okay, what if I go over 2? So 1, 1. What if I go over 2? 2 cubed? Okay, that's too far. Don't do that. What if I go over 2? 2 cubed is 8. So I'm going to go up 8. So in the same way, 1, 1, 2, down 8. And you know what? You're going to see this general shape. So instead of 4, okay, it's 8. So this thing grows way faster. But this is the shape. This is the general shape of a simple cubic. Now, I know as soon as we throw in all this other stuff, the x's, okay, it's going to change its shape. But if it's a triple root, this one is, right? If it's a triple root, it's going to be this kind of shape. It's going to be a change in curvature. So let's graph this thing. Well, first off, let's describe it. Okay, so I know it's a cubic. What are the transformations? Okay, it's upside down and it has a vertical stretch of a half. Okay, so vertical stretch is negative 1/2. And I know that that means it's upside down. So in other words, it's going to go down like that instead of like a regular one would be this kind of shape going up to positive infinity. Now it's going to go down to negative infinity. I know it's a vertical stretch because it's not touching the x. It was originally touching the y if this was over here as negative 2. Okay, I know it's up 3 and it's moving 1 to the right. So the vertex, really, the center of the graph, is going to be 1 to the right and up 3. So 1, 3. So I can just start at my vertex and draw this thing with a stretch of negative 1/2. Now we could do it as a table. You know what? Let's do 3 simple points. Normally, if it's this is centered at the origin, right? So I'm going to do 0, 0. Right? And I'm simply going to move it. Move it first? No. Do you want to stretch it first or do you want to move it? Well, if we know what the shape is and we know it's just going to be moving 1 to the right and up 3, I can just do the exact same thing and I'll just draw it based upon my new vertex. Okay, so if I'm going to move it 1, 3 vertex, let's move it that way. I know I'm just adding on 1 to the x and I'm adding on 3 to the y. And then the vertical stretch is negative 1/2. Vertical stretch, negative 1/2. Oh, that's terrible. There we go. I'm stretching the vertical. So not the x value, the y value. Okay, so this is going to be negative 1/2 times 3. So this becomes 1, negative 3 over 2. Done. There's my vertex. Or is it? Is it? The vertex is the center point here. Let's not bother using this. It's easier to just draw this thing by hand. I know where the vertex, oh, that's what it is. If I want to actually use my table, I need to do the stretches in order, right? I got to do the negative 1/2 stretch, and then I have to move my vertex. No. We know it's just going to be over 1 and up 3. Let's just draw it this way. There's my vertex. So normally it's going to be this kind of shape, right? Great. There's my vertex, just like a parabola. Over 1, up what? What's the stretch? The stretch is negative a half. Over 1, down a half. Right? Let's make this bigger. Can I go 3? There we go. That'll be way nicer. So I'm going to go over 1, up a half. Right? Because it's going to be, instead of going this shape, I'm flipping it upside down. And then 2, 8. Okay, so over 2, 1, 2, 3, 4. Over 2, 1, 2, 3, 4. See, I can see the general shape of this thing. And it's basically a triple, all of these are together. So really this is going to be, come on. And then the rest of it just goes down based upon the shape of the cubic. All I'm doing is I'm really just, I don't know what the y-intercept is. It's not that hard to figure out. I could actually plug in the x value of 0. What do we get? We would get negative 1 cubed, which is negative 1. So I'm going to get positive a half plus 3, which is 3.5, 4. No, that's right. Wrong. When the x value is 0. Hang on, what would I get? I messed this up. Up 3. I moved my vertex in the wrong place. Ah, you idiot. Okay, good. Let's go back. I wish I could go back and edit this. Over 1, up 3. There we go. There is 1, 2, 3, 4. 1, 2. Normally it's 8, but I'm going to go 1, 2, 3, 4. That's why it makes sense. So this is the shape of my graph. That's why I get the y-intercept at 3.5. And the x-intercept is somewhere in there, but the x-intercept is not really all that important. There we go. So that's the general shape of this thing. Okay, is that super duper important? Not really. It's just that you don't need to expand this thing all out and figure out how to factor it, because the factors aren't really all that important. It's based upon its shape. So this is it. The last part of the chapter, and then the rest of it is just review. So hopefully you guys can get some of this stuff finished up this week, and then let's get this test over and done with, and that's it. That is the end of the course, and then summer begins. Alrighty, good luck with these.